Off the coast of Odisha, on APJ Abdul Kalam Island, the build-up to the launch was kept quiet. The resulting test, however, immediately caught the attention of the global community. The government officially codenamed the test Mission Divyastra, and the success of the operation soon dominated national defense headlines. At the center of those reports was this specific piece of hardware, a highly advanced variant of the Gr2 missile. India already maintains a vast arsenal of capable missiles. This led the Defense Research and Development Organization, the DRDO, to focus this specific Gr2 variant on a specialized tactical requirement. To understand that requirement, we have to look at the mechanics of traditional ballistic missiles. Usually, a launch vehicle carries a single payload along a parabolic trajectory to strike one target. Modern defense networks exploit this predictable path. An enemy anti-missile shield tracks that single incoming line and deploys an interceptor to neutralize it mid-air. This puts the attacking force at a severe mathematical disadvantage. To guarantee a successful strike against a heavily defended target, a military would need to launch an immense, unsustainable barrage of missiles, hoping just one slips through the net. To maintain a credible threat against these shields, a weapon must be capable of overwhelming the defense grid from within a single launch vehicle. The engineering solution to that problem is MIRV, Multiple Independently Targetable Reentry Vehicle Technology. The process starts with a standard ascent. The missile carries the payload out of the lower atmosphere and into the vacuum of space, keeping its true nature hidden inside the nose cone. Once in space, the main missile bus opens and dispenses several smaller independent warheads rather than a single explosive. During the re-entry phase, each individual node calculates its own distinct trajectory. This allows the warheads to lock onto different geographical coordinates and strike them simultaneously. Verifying this performance requires intense coordination. A network of land-based radars and naval tracking ships monitored the Mission Divyastra test to confirm every warhead's precise impact. For an adversary, this creates an immense defensive challenge. Intercepting the primary missile in space is difficult, and once the warheads branch out, they require an overwhelmingly complex defense grid to stop. Beyond the branching payload, the delivery mechanism itself possesses an extreme operational range. Looking at India's legacy arsenal, we can see the geographical reach of earlier models. The Agni-1 through Agni-4 missiles were limited to strike radiuses between 700 and 3,500 kilometers. The Agni-5 significantly extends that boundary, pushing the strike radius out to 5,000 kilometers. Pairing a 5,000-kilometer reach with MIRV technology extends India's strategic influence across a much wider geography, allowing for a flexible response from a secure launch site. This milestone was achieved completely in-house, driven by the DRDO and a vast network of domestic defense manufacturing partners. Following the test, Defense Minister Rajnath Singh issued public congratulations to the scientists and military personnel who spent years developing the system. This technology is now integrating directly into the Indian Armed Forces, elevating the operational readiness of the national defense infrastructure. A weapon this devastating is built for strategic deterrence. It creates a mathematical certainty of retaliation, discouraging an adversary from ever attempting a first strike. Mission Divyastra marks India's entry into an elite tier of global military powers, establishing a fortified defensive posture